Hello everyone, my name is P. Baravas of ECA section and my topic is Unitary matrix pencils in signal processing. So introduction about my topic. Wideband arrays have been widely used in many applications such as communication and radar systems. This is a class of arrays with broadband frequency variant patterns which can be used for receiving. Broadband techniques have been developed by desired wideband patterns such as Fourier transform technique, the stochastic approach, and convex optimization methods. Despite the success of these techniques, they mainly focus on optimization of element excitation weights. Hence, most of them prefix element positions with half wavelength spacing in the highest frequency. The dense element distribution is used to achieve desired wideband FL patterns, which also increases the antenna number and the whole hardware system cost. The next topic is UMP with FI pattern, wideband array synthesis problems. Assume a linear array owning M elements with series of excitations converting wideband frequency. The array factor in one tested frequency point can be written as Fu equals to R of exponential j to x FDU by C, where represent the complex estimation coefficient of the ith element with coordinate corresponding to the kth sample frequency. C is the speed of the lead parameter, u equals to cos, where E is the desired scanning angle of array patterns. The desired Fi patterns may be synthesized with Taylor Chebyshev patterns with initial common locations but different excitations. Within band, the synthesis problem is to search the minimal system, and there is the equation for the thing, and Q takes a minimax value. Here Q is the reconstructed minimum element and is a small tolerance between the sparse linear array and ordinary one. M is the initial number of array elements and K is the number of tested frequency. D and V are the location and excitation of the qth element for the sparse linear array, where the superscript F is the kth tested frequency point. And next topic is wideband EMP synthesis method. Previously, a non-iterative synthesis technique based on the MPM to synthesize non-uniformly spaced arrays with few elements. Extended MPM and FBM-PM was same poles that correspond to FL element positions in the synthesis method of MPM or FBM-PM. The complex unitary matrix of sampled pattern data contributes to the complex valued elements positions. The MPM takes the real part of D to B estimate element positions by neglecting the non-physical imaginary part of D. The technique may approximate successfully the pattern of shaped beam patterns or multiple patterns, through the problem can be partly settled by placing a locally sufficient constraint for limiting the poles unit circle in the FBM-PM synthesis work. It cannot guarantee all poles on the unit circle, especially when dealing multiple shaped beam patterns. There are still approximate treatments for the poles outside the unit circle. The imaginary effects on the synthesis of sparse patterns cannot be absolutely neglected or estimated. Now we present a desired wideband patterns, which directly builds the relationship between the real valued and generalized eigenvalues and real element positions. The array factor in the kth register frequency point can be formulated as f of u equals to zmr of kz, where b equals to 2 f by c and uk equals to bu. To explore the EMP method into the synthesis of wideband Fi patterns, we set u and u where nk n by 2 minus nk2 plus n for tested k frequency points, where dmax equals to max and umax equals to the data of pattern can be written as k and k by z, where the pattern data equals to in different frequencies have different lengths. The sampling strategy guarantees the poles object not to vary with frequency. It is different from the previous synthesis work. Direction and corresponding poles are equals to 12 by FDC varying with E frequency. The sampling strategy is extended to the UMP method to estimate the band common poles corresponding to invariant element positions of wideband frequencies. The sampled pattern data of a frequency of block Hankel matrix for linear array can be constructed as below. X equals to x of 1 x question mark where k is l plus 1 x of n minus l plus 1 where x of t composite Hankel matrix composed of k tested frequency pattern data at the zero beam direction without extra reconstructing of complex conjugate Hankel matrices. The difference between x and is that the combination of phase excitation weight. The UMP method is proposed here by directly building the relationship between the real valued generalized eigenvalues and element positions. A unitary transform corresponding to the UMP method is exploited to convert the complex matrix X into real one for the reduction of computing burden on the synthesis of linear array in wideband as below, where D is the real valued matrix, both H1, H2 are unitary matrix with sparse structure, where an even odd dimensional form of unitary matrix, where D is D into D identity matrix. 2D is an exchange matrix with size D into D as below. DS denotes a central Hermitian matrix as a form of DCH XE X2 where L plus 1 and E2 N4. The singular value decomposition procedure for the complex matrix X is replaced by the real valued matrix D where ES is a diagonal matrix with singular values for a linear array with n elements. They actually exist in non-zero singular values. The number of principal singular values less than 2 and arbitrary labia. If sigma S is a diagonal matrix with singular values for a linear with n elements, there actually exist n non-zero singular values. The number of principal singular values is less than n, and even approximate lower rank matrix D which corresponds to the Fi pattern can be obtained by combining corresponding left and right singular vectors with only q singular values. Here's the equation for q singular values. Poles corresponding to the real valued generalized eigenvalues can be obtained by the matrix pair where L is an LL identity matrix tan. Consequently, an alternative way with higher efficiency of finding the poles corresponding to generalized eigenvalues can be obtained by tan AD by 2 RE of x UQ equals to AM of x UQ. Consequently, an alternative way with higher efficiency of finding the poles corresponding to generalized eigenvalues can be obtained by tan of AD by 2 Rex UO equals to IM of UQ, where UO is the only Q singular vectors of US. The sparse locations of reconstructed array elements are given as below. Once the locations of D are obtained by the existence stations of W of Q equals to 1, 2 so on Q, within all tested insert frequency points can be computed in series by following questions. F of k equals to z of k into w of k, f of k minus n by 2 into minus n by 2 plus so on n by s, where z1 is agdu I equals to 1 comma q comma so on q. A new tactics is also exploited to avoid two small array intervals between array elements with following combination technique when d minus d of inverse ad is then AD, where D and D plus 1 are reconstructed locations of adjacent array elements at this allowed minimum distance between two array elements, which can be adjusted by requirements of antenna element size, and C plus 1 are combination weights within wideband frequency, where D1, D and D plus 1 are reconstructed locations of adjacent array elements. AD is allowed minimum distance between two array elements, which can be adjusted by requirements of antenna element. C and C1 plus 1 are combination weights within wideband frequency, and down you can see the equation of C1 equals to 1 by sigma k if k is equals to 1 into V W I k whole square by I k whole square plus W I plus 1 k whole square, and the second C I plus 1 equals to 1 by k sigma of k equals to 1 w of t I plus 1 k whole square by w I k square plus w I plus 1 k square, where k equals to 1 by 2 is the excitation of the ith element in kth point. The excitations of different frequencies are recalculated by the final element positions to validate the pattern synthesis accuracy performance. The wideband frequency of the normalization error is defined as the equation. In the down you can see it. And with this I end my session, and thank you.